Good afternoon, everyone. This is Dr. Daniel Barth with the How Do You Know program. This is episode 92. Welcome back. Today's program is brought to you by Star Mentor. This is the latest thing. If you're looking for something to teach you the intros, ins and outs to astronomy, how to read the sky, how to use a star map, use a telescope, this is your ticket. It's available on Amazon. And the other book I'd like to mention to you today is Astronomy for Educators. You can put that book into any search engine. It will come up on top. It is the world's most popular astronomy activity manual. And if you're looking for astronomy activities for the eclipse, for kids, for outreach, for yourself, or if you know a teacher, you can look up Astronomy for Educators on any search engine, download it for free, and I hope you'll do that today. And before we go on to our program today, we have astronomy in the news. So, kilonova. How many of you have heard of a kilonova? Well, we've heard of star novas and supernovas. Kilonovas are much smaller. Kilonovas occur when neutron stars merge, and that's a very violent event. But we know that the nucleosynthesis of lighter elements such as helium, carbon, oxygen, and all of the periodic table up to iron, synthesis of those elements occurs in standard stars just like our sun. When a supernova goes off, it scatters those elements and also provides the energy to fuse additional heavier elements up the periodic table. We used to think that all heavy elements were formed in supernova explosions, but we no longer believe that's true. Newer research shows that heavy elements such as gold and platinum and others are much more likely to occur in kilonova situations. It seems that the extremely high energy and temperatures of a supernova not only forge elements like gold and platinum, but also destroy them. Among the special elements which we think are only formed in kilonovas include bromine and iodine. Now, if you're familiar with your basic biology, bromine and iodine are both essential minerals. The body requires them for health. It does not synthesize them, and it must get them from food sources. And the interesting thing, these particular elements, which are necessary for life, could not have come from standard nova. So these little kilonova, it turns out, are essential for life because they make elements which are key mediators in chemical reactions inside the body. They're also key to producing catalysts, which allows biological reactions to work. In another news item, NASA is testing a space-rated nuclear reactor. Now, when we mention nuclear power, a lot of people kind of get uneasy. Oh, nuclear power, isn't that bad? Are we going to have another Chernobyl? No, actually, nuclear power is the most carbon neutral, it's the only completely carbon neutral energy source we have, and it's extraordinarily safe. The amount of danger and accidents that we have per million kilowatts produced is very, very tiny compared to coal, gas, and others. Well, NASA is calling for the plans to do a one-year test in the early 2030s on a new nuclear fission reactor that's space-rated. In other words, this is a reactor that we could pack up on a spacecraft, send to the moon, send to Mars, deploy it, set it up, and get it started. And power is essential for manned space exploration. If you think about manned space exploration beyond Earth orbit, 12 men have landed on the moon, and none of them stayed for more than a few days. And of course, the moon is infamous because it has a 15-hour or 15-day long day cycle, and then basically 15 more days of darkness. So renewables on the moon, not really much of an option. Solar doesn't work half the time. There's no wind, there's no air, there's no geothermal. Nuclear is going to be our best option for a safe, stable, consistent power source, because remember, when we're someplace like the moon or Mars, we don't just have to have power to run our devices, we also have to stay warm. And staying warm in the lunar night or just in the Martian environment is a tough challenge indeed. So we'll look forward to this experiment with the new nuclear reactor, and it's supposed to power an Artemis moon base for extended, sustained human presence. And this reactor, NASA believes, can power up and run for at least 10 years at a go, which is really promising. And in our final item in the news today, we have Mars, and two separate items here came up. Mars is more tectonically active than we thought. One of the things that we believed of Mars, because it shows little to no evidence of plate tectonics, is that perhaps Mars was geologically dead today. We think it's actually more tectonically active than we thought. The Eridania region is now known to be home to 63 newly discovered examples of volcanic vents and cones. And we believe that Eridania was home to a large body of water, a shallow sea, if you wish, called the Eridania Paleo Lake. That's what they've named it. This was up to 1 mile deep. Doesn't sound much like a lake to me, more like a shallow sea. 1 mile deep, and it had volcanic vents on its floor, perhaps as much as 1.2 kilometers deep. Now, if you know anything about volcanic vents on the ocean floor here on Earth, you know that they are all home to unique communities of life forms. We have black smoker vents in the Pacific, and we have volcanic ridge vents in the Atlantic. All of these areas of relatively warm, nutrient-rich water on the bottom of a very cold sea, these islands of warmth and nutrients are home to lots of exotic animals, some of which are not even oxygen metabolizers. Some of the worms and crabs and other things that live down at these vents are sulfur-breathing organisms rather than oxygen-breathing organisms. And we've also found in other research, scientists have just announced in the last week or so that a new supervolcano has been discovered on Mars. It's located in Noctis Labyrinthus, which is the far western edge of the Mariners Valley. And you go a little bit further west, and you get the Tharsis Plateau, where you have all of the major Martian volcanoes, including, of course, Olympus Mons. This new volcano is in Noctis Labyrinthus, so it's right off the western edge, so it's kind of the first volcano in this chain. Why didn't we discover it before? It's buried under a glacier and dust. So we found that this new area may be an exciting place to land and search for signs of past life on Mars. We'll look for more information on that coming up soon. Now, let's go on to today's primary topic. Are dwarf galaxies endangered? Okay, I admit it, it's a little bit of a clickbait title. Dwarf galaxies endangered, are they going to appear on the EPA list of endangered critters? No, in fact, they are not. But when we say endangered, what do we mean? If we think of a normal healthy galaxy, such as the Milky Way, Andromeda, Triangulum, any of those in our local cluster, these are spiral arm galaxies. Some are elliptical galaxies, but in every case, they contain hundreds of billions of stars. Dwarf galaxies are substantially smaller. And whereas a normal, healthy, large galaxy like the Milky Way is constantly producing new stars. And we can see this, we see it primarily in the spiral arms, where you have high density and stars form, and you get a lot of new, young, blue, hot stars. And we can see these by watching galaxies in blue light. Dwarf galaxies are very different, and they don't do much in the way of star formation. Turns out, dwarf galaxies are perfect targets for the James Webb Space Telescope. And the JWST is doing a new observing program called PEARLS. Prime Extragalactic Areas for Reionization and Lensing Science. Those acronym folks really go out on a limb with some of these. It's great stuff. The PEARLS program recently discovered a quenched dwarf galaxy. We've talked about quenched galaxies on this program before. Longtime fans will remember. These are galaxies where star formation has halted. And we found this lovely quenched dwarf galaxy. It was serendipitous. They weren't looking for it. Kind of like when you're looking for your car keys and you go, oh, look, here's my wallet. It was kind of like that. They were looking at a galaxy cluster, and this galaxy cluster is about 98 million light years away, or 98 megalight years. When JWST was looking at this dwarf galaxy, and what did they call it? PEARLS DG, or PEARLS Dwarf Galaxy. There you go. Well, they discovered that, oh, look at this faint fuzzy spot. We're looking at this cluster of galaxies. They found this. Well, this new dwarf galaxy, it's not making any new stars. None at all. And if it's not making new stars, then new stars, because they're bright and they're blue, they tend to put out a lot of light, a lot of glare, and they make it hard to see individual stars in galaxies. If you want to see an individual star in a galaxy like Andromeda, you don't want to look in one of the spiral arms. You want to look between them, where the glare is less and you have a better chance of spotting your target. Well, in this new dwarf galaxy, JWST is seeing red giant stars, and not just any red giants. They're seeing red giant branch stars, or RGB stars. What's nice about RGB stars? The nice thing about them is that they're very bright in the infrared, which makes them perfect targets for the James Webb Space Telescope and its infrared cameras. Now, the other reason we're looking at dwarf stars with JWST, with dwarf galaxies give us a better chance to see individual stars that are outside of our galaxy and give us a chance to take a look and do analysis on these individual stars 100 megalight years away. Just incredible. And when we say dwarf galaxies contain fewer stars than the Milky Way or a typical barred spiral, we're not just talking by a little bit. Milky Way, Andromeda, and other similar class galaxies, about 400 to 500 billion stars, 500 billion. Well, you take a look at that number and you say, wow, 500 billion's a lot. Well, yes and no. We also know from research that red dwarf stars are massively undercounted. They're small, they're dim, they're harder to see, they're easy to lose in the glare of other bright, young, hot stars. And so we think that this 400 to 500 billion number, at least I think, it may be significantly undercounted. But a typical dwarf galaxy contains perhaps 100 million stars. What a paltry amount of stars. 0.02 or 0.02 of the star count of a typical galaxy like the Milky Way. So we're talking about a relatively tiny, pocket size for your convenience, 100 million stars in a dwarf galaxy. Why, you could practically put that on a keychain. So how many stars and of what kind do you get in a dwarf galaxy? It turns out that depends on how it was formed. And we're going to take a look at several methods because the scientists researching this believe they found a new way that dwarf galaxies may have formed. The first method is called the clumping method. Now, this basically, how many of you all have been out looking at the Orion Nebula this winter and spring? It's beautiful. It's one of the most famous astronomical sights, and it, in fact, is a good example of clumping. What we've got in Orion is a large molecular cloud of gas and dust that's large enough that its own gravity is causing it to compress, not just in general for the entire cloud, but in small regions where it forms stars. And we've talked about how the Orion Nebula is forming things like Jupiter-sized binary objects, as well as stars of all different sizes and classes. But whenever we have a big enough cloud of gas and dust, this can, in fact, form a dwarf galaxy of perhaps just 100 million stars or so. And we think most of this clumping formation happened earlier in the universe, relatively soon after the Big Bang. And the reason is that at that time, shortly after the Big Bang, the universe was a much denser place than it is now. Why, if you go outside the solar system to where the Voyager spacecraft is, you could throw a baseball in practically any direction you'd like, and to say it would never hit anything, probably reasonably accurate, because the universe today is very empty. But shortly after the Big Bang, the average density in the universe was much higher, meaning gravitational effects were much stronger, and these molecular clouds of gas and dust could easily clump down and condense and form stars and create dwarf galaxies. The Pearls DG may or may not have been one of these. The other method, the modern method, because obviously clumping isn't happening anymore, the universe just isn't that dense. It's not that we don't have clumping, but it tends to be smaller and more regional, like the Orion Nebula. The collision method is the modern method. This happens when two large galaxies, like the Milky Way and Andromeda, collide together. Now, this isn't like an automobile collision. When two galaxies collide together, the first thing you have to realize is that galaxies are mostly empty space. Although we see them as large and bright and having enormous masses and hundreds of millions of stars, galaxies just are mostly empty space. Two galaxies colliding is like two clouds of gnats colliding on a summer afternoon. But there's a lot more gravitational interaction when galaxies collide than when clouds of flies collide. And because when galaxies collide, they tend to stir each other up, and they tend to strip off long streamers of gas, dust, and actual entire solar systems, each from the other. When galaxies have collided, we can often see streamers of gas, dust, and new stars streaming away from the point of collision. These streamers often provide, similar to the early universe, regions of relatively dense clouds of gas, dust, and some new stars, and these streamers can form into dwarf galaxies. Does this happen? Yes, it does. Galaxies like the Milky Way were formed by, many of them, by assembly of smaller galaxies into larger. And the Milky Way itself has 14 identified dwarf galaxies that are orbiting around it. And it's almost certain that all of these formed during collision events between the Milky Way and other galaxies which the Milky Way has absorbed. The two most famous dwarf galaxies associated with the Milky Way, of course, are the Magellanic Clouds, the Greater and Lesser Magellanic Clouds. Now, these clever folks who are looking at these dwarf galaxies with the Pearl survey, they believe they have come up with a new method of dwarf galaxy formation, and they're christening it the primordial method. Now, they've been mining data You realize that all these space probes, folks, produce data, and they give us this fire hose gush of data, and scientists continue to sample that for years and decades to come. We're still analyzing data that came from the Apollo moon missions 50 years ago. We're still analyzing data from Voyager, from Pioneer, from Mariner, and Viking. These spacecraft of decades ago have left us with lots of gigabytes of data, which scientists still comb through and use as data sets to test their theories today. Working with NASA's Galaxy Evolution Explorer, they think they have a new method for galaxy formation called the primordial. So this Galaxy Evolution Explorer, also called GALEX or GALEX, G-A-L-E-X, this was optional from operational from 2003 to 2013. So 10 years worth of data before being decommissioned, and here we are 11 years later still getting good data and new science from it. This indicates that dwarf galaxies may form today from primordial gas, that is helium, hydrogen, and lithium, left over from early galaxy formation. So you have the Big Bang. Keep in mind, the Big Bang produced only 3 elements. Hydrogen in great quantity, about 74% of the material formed, helium, the most abundant. Hydrogen, about 24%, and the remaining 1.5 to 2% was lithium. So these 3 are the primordial. Lithium isn't terribly stable, so 13 billion years later, there's not much of that left in primordial clouds. They're primarily hydrogen, helium, which are both stable atoms. So when we're looking at this primordial gas, how is it different from galaxies formed from clouds of gas today? Or how will the stars be different from clouds forming stars like in the Orion Nebula today? And the answer is that primordial gas has virtually no metallic elements. Now I'm going to put a little finger quotes around the term metallic elements here, friends, because when our astronomers and astrophysicists talk about metallic, they're talking about anything heavier than helium. So basically they're talking about elements which have been formed in more modern times, i.e. post-Big Bang, in stars by nucleosynthesis. So everything from lithium on up through uranium, etc., all of those are considered metals by your astrophysics people. And this primordial gas doesn't contain any. There have been no stars there to form this material, and the Big Bang didn't do it. So the other interesting thing, these regions show no evidence of dark matter. We've talked about dark matter a number of times on the program, and we know that dark matter is a theoretical idea. No one's ever found it. But it's this theoretical idea that dark matter would supply the gravitational field necessary to help galaxies form and stay together. Well, these primordial gas clouds don't have any of that. Have we ever seen this new kind of dwarf galaxy formation? Turns out we have. Something called the Leo ring. The Leo ring is a very large ring of primordial gas, and it surrounds the Leo galaxy cluster. That's M96 for those of you hot to get out tonight with your telescopes and find it. M96, the Leo galaxy cluster, and some of you may have looked at the Leo triplet and other things like that. When that galaxy cluster formed, it left a ring, if you will, of primordial gas with virtually no metallicity, nothing above helium. And this ring of gas was only discovered by radio astronomers in the early 1980s, so it's relatively recent. GALEX, the Galaxy Explorer telescope from NASA, has revealed dwarf galaxies in this ring. And if they're dwarf galaxies in this ring, they indicate no metal, no dark matter, which gives us a pretty good idea that these galaxies had to have formed in the ring from primordial gas. Had they formed from material that formed the rest of the Leo galaxies, or from gas and material left over, it would all virtually certain that would be contaminated with metallic elements from supernovae in the galaxies themselves. And we find none of this. So this is leftover primordial gas. And when we look at this with the Galex telescope, scientists were able to detect a UV signature of massive star formation. So these dwarf galaxies were, in fact, forming stars from this primordial material. Interestingly, we're not sure what these stars, what type of population these stars actually belong to. We've talked about star populations before, too, where population 1 is the modern stars, like our sun, stuff formed within the last 5 to 7 billion years. Population 2 stars, and then we get to population 3 stars, which are the oldest. Those stars would have been formed in the very early universe, and they would have virtually no metallicity, because when these stars were forming, and our question now is, my question to these folks have to be, well, gee, are these population 1 stars? Why? Population 1 stars are known to be, or thought to be by theory, extraordinarily massive, up to 1,000 solar masses. Blue giant stars, which are hard to form, burn fast, and die very, very quickly in 1 million years or less. So this is research that needs to be done. Nobody's ever seen a population 1 star before, because we were looking at high Z numbers. We were looking for stuff back far away as 12 to 13 billion light years away from us. It turns out maybe we're looking too far from home. Maybe if we look at things like the Leo gas ring and dwarf galaxies forming there, we may find some population 1 stars in the modern universe, which would be very interesting. But what about dwarf galaxies that are modern, dwarf galaxies we see today, like those surrounding the Milky Way and those we see even in galaxy clusters? They all seem to lack young stars. When we look at a dwarf galaxy, similar to when we look at a globular cluster, we see stars that are extraordinarily old. We don't see, by and large, the young blue hot stars that are a few million years old and burning very quickly and going through their main sequence and going boom and dying young. What we tend to see is much older stars, red giant stars and other stars which have been around for 8 to 10 or even billion years or even longer. So why don't these dwarf galaxies have these young stars? Because of course, young stars are the lifeblood of a galaxy. Producing new young stars produces new elements, new material for planets. Well, we think there are a number of mechanisms that gets rid of these young stars in these dwarf galaxies. Turns them into sort of senior citizen mobile home parks for older stars, where the young aren't really wanted. Yeah, I know, terrible joke, wait, there's more. So, the first method is called tidal stripping. This is when a dwarf galaxy orbits or interacts with a much larger, big, powerful galaxy like the Milky Way or Andromeda. When this happens, the powerful gravitational field of the big galaxy is going to pull away gas and dust and even entire star systems from the smaller dwarf galaxy. It turns out that the gravitational binding that the dwarf galaxy has on light things like clouds of gas is quite weak, and the gravitational tug from the big galaxy can be enough to strip those materials. Scientists have found streamers of gas, dust, and entire solar systems being stripped from the greater and lesser Magellanic Clouds, and we're talking streamers tens of thousands of light years long. And this material is being pulled off of these dwarf galaxies And because it's stripping the gas and the dust and even the young star systems, it's stopping star formation in these dwarf galaxies. No gas, no dust, no new young stars. All you've got is the old ones you started with. The second method of getting rid of these materials and stopping a galaxy, dwarf galaxy, from forming new stars is something called ram pressure stripping. So, what's ram pressure? Well, the easiest way I can explain ram pressure to you is something we've all done as kids. When you were in the backseat of the car when you were a kid. Okay. There we go.
I let it go, and it got worse.
There we go. Is that better?
Yes.
Much better. Sorry about that, folks. Anyway, ram pressure stripping. If you were in the car as a kid with your parents, didn't you at some point stick your hand out the window and go, ooh, look, I can make my hand fly like a bird and feel the pressure of the wind while the car was going down the road? This is exactly ram pressure stripping. When a dwarf galaxy travels through a galaxy cluster, that galaxy cluster has residual intra-cluster gas. It has gas and dust left over from the galaxy forming process. You're flying through this cluster, you're essentially flying through an atmosphere. Now, nobody's going to stick their hand out and do that game, but what we find is, again, if the wind pressure on that galaxy is greater than the gravitational tug holding clouds of gas together, the gas will essentially, quite literally, be blown away. So this happens when the galaxy, the dwarf, is traveling through a galaxy cluster, and it eventually dies in that it no longer has the ability to produce new stars. So it's no longer a functioning galaxy, it's just a cluster of stars waiting to die. Finally, we have strangulation. Gee, doesn't this sound great? Tidal stripping, ram pressure stripping, and strangulation. This occurs when you have an active galactic nucleus in your region. It's bad to have an AGN anywhere near you. An active galactic nucleus, friends, is actually a supermassive black hole that's actively feeding as much as 1 solar mass of material a day, or even more. We also know these as quasars. When you have an active galactic nuclei, this can create, or does create, an accretion ring which heats up to millions of degrees, and that causes a couple of things: an immense amount of radiation up through ultraviolet and even gamma, and it also causes, by the extreme heat, a very violent, effectively, solar wind that comes off the accretion disk. It's not a true solar wind which comes from the surface of a star. Nothing comes from the surface of a black hole, but it does, maybe it's an accretion disk wind. It comes off that accretion disk, and this solar wind, if you will, or accretion disk wind, blows the gas out of the dwarf galaxy into the intergalactic environment and essentially shuts off the gas formation. Does this sort of thing really happen? We know it does, because we have an analogous process. When a young star is forming and it has an accretion disk around it where protoplanets are forming, the planets continue to form until the star gets ignited with fusion, it gets hot, its solar wind kicks off, and it then blows away the dust and gas, and planet formation essentially stops. So we see this analog process at different scales going on. So we look at this, and we start to realize that a couple of things here. First of all, dwarf galaxies, like dwarf stars, may be, and probably are in this scientist's opinion, a lot more common than we used to think. And like I said, the Milky Way has 14 dwarf galaxies orbiting it, and it's difficult to find dwarf galaxies around large galaxies that are very far away. If they're more than the neighborhood a couple million light years away, it gets really difficult to detect those dwarf galaxies and pick them out from the glare of a active galaxy with lots of new stars and bright blue light coming from it. And so we see other galaxies nearby. They have their own dwarf populations, but as we say, we don't think we've found them all. The other thing is that dwarf galaxies may be a lot more common. Look at the discovery they just made. They weren't looking for this dwarf galaxy, the Pearls GG. They weren't hunting for it. They stumbled over it while they were looking for something else. And the reason nobody was hunting for it, it was so faint it didn't appear until they got hundreds of hours of data and then processed it and said, wait, there's this fuzzy spot here. You ever gone comet hunting, friends? Yeah, it's much the same. So this idea, are dwarf galaxies endangered? It seems like their young active phase where they're actually making stars is going to be quite short. Maybe as short as 1 billion years. How tragic to die after only 1 billion years. It's not that these dwarf galaxies aren't going to live on, it's just they're not in the process of renewing themselves. It's like if you had a population, let's say, of dodo birds on an island. You discovered them and you're like, oh, we've discovered these dodo birds. We're going to bring dodo birds back. But then you realize, oh, wait, all these dodo birds are like 50, 60 years old. They're beyond the age of reproduction. The population is just going to dwindle and die. It's never going to grow anymore. So when we think about galaxies, we have to remember that they're not single things. They're aggregates of many millions. And when we look at the lifetime of such a thing, we're looking for, gee, are they producing new stars or not? Or are they just a collection of faint old stars waiting to die? That's where we're going to wrap up How Do You Know this week. And we hope you'll be back, and we'll be on a more regular schedule now again. And we'll be bringing How Do You Know to you regularly every week.
All right. Is that it?
That's all for today, friends, and thank you for watching. Appreciate it.